Have you ever found yourself just standing there in the dairy aisle, staring at that endless wall of cartons, and wondering, does the specific breed of the cow actually change the milk inside? I mean, is it a real biological difference, or is it all just clever marketing? Well, before you reach for your usual gallon, let's look past the packaging and find out what's actually going on inside your glass. Because, get this, here's a staggering number to kick things off: 65%. According to the data, 65% of the global population has some degree of lactose intolerance. That is a massive number. It means that for the majority of us on this planet, understanding the literal science of milk isn't just a matter of casual curiosity. It's absolutely vital for our daily comfort and our digestive health. So, welcome to this explainer. Today, we're stepping right past those flashy marketing claims to see how milk actually works. We're going to break down the biochemistry, trace the processing methods, and tackle some of the most heavily debated health claims you'll encounter in the dairy aisle. Okay, let's dive into this. Here is how we're mapping out the dairy aisle today. First, we'll look at the blueprint of milk. Then, we'll spend some time navigating lactose and digestion. Third, we'll trace the exact journey from farm to fridge. Fourth, we'll examine the fortification factor. And finally, we'll impartially unpack hormones and health claims. Let's start right at the foundation with Section 1, the blueprint of milk. So, while a typical glass of whole cow's milk is about 88% water, it packs around 8 grams of really high-quality protein, and this is divided into two major families. First up is casein, making up about 80% of that protein. These are insoluble proteins, and they're incredible at boosting your body's absorption of minerals like calcium. The remaining 20%? That's whey. It's highly soluble and super rich in branched-chain amino acids. Actually, whey is the exact reason athletes rely on it so heavily for muscle building. Moving right along to Section 2, navigating lactose and digestion. And this brilliantly illustrates what happens to lactose during processing. The way milk is processed drastically changes how much milk sugar, or lactose, actually makes it to your stomach. You see, if you lack the lactase enzyme, you get that classic bloating. A standard cup of regular whole milk has about 12 grams of lactose. But when bacteria ferment that lactose to make Greek yogurt, it drops down to about 8 or 9 grams. And for harder cheeses like Parmesan, well, the liquid whey takes the lactose right out with it during processing, leaving less than 1,000th of a gram per ounce. So yes, your cheese addiction is actually science approved. But wait, what if your digestive issues aren't actually caused by lactose at all? Some researchers believe the culprit might be something much more microscopic. Meet BCM7. BCM7 is an opioid peptide that gets released during the digestion of a very specific type of milk protein known as A1 beta-casein. And let me tell you, this single microscopic peptide is the root of a massive debate in the dairy world right now. Which brings us all the way back to our opening question. Does the breed of the cow actually matter? The answer is yes. Cows originally from Northern Europe, like Holsteins, generally produce milk that's high in that A1 protein. But breeds from the Channel Islands, like Jerseys and Guernseys, well, they produce A2 milk. And here's the kicker. When you digest A2 milk, that BCM7 peptide isn't released. Clinical studies do show that A2 milk might lead to less digestive discomfort for some people. Now, you might have heard some pretty scary claims linking A1 milk to severe conditions like heart disease or type 1 diabetes. But it is absolutely crucial to note that the data behind those severe claims is purely observational, or just from test tube studies, and it currently lacks the strong human clinical trials needed to actually prove causation. All right, let's transition to Section 3, from farm to fridge. Let's move to the commercial filtration pipeline and see how this builds, because the liquid leaving the farm is rarely the exact same liquid you pour over your morning cereal. When raw milk arrives at a plant, it passes through incredibly precise membrane filters. It might go through reverse osmosis, which allows literally only water to pass, or nanofiltration to pull out specific minerals. Then there's ultrafiltration, which separates the skim milk to concentrate those proteins and fats, while microfiltration acts as the final bouncer, using a more open membrane to completely strip out unwanted spores and bacteria. Now, beyond all that filtration, commercial milk undergoes two totally distinct physical processes. Pasteurization is strictly about safety. It involves rapidly heating the milk to kill harmful bacteria, while leaving the overall nutrition intact. Homogenization, on the other hand, is entirely about texture. By pumping milks through really narrow pipes at immense pressure, the naturally clumping fat globules are violently broken apart. This is exactly what prevents the cream from separating and rising to the top, and it gives modern milk its uniform, rich consistency. That processing leads us perfectly into Section 4, the fortification factor. Now, what's really interesting about this slide is the dramatic difference in vitamin D. Unfortified milk naturally contains 0% of your daily vitamin D, zero. But through public health strategies, which were originally developed to eradicate bone-weakening diseases like rickets, by the way, vitamin D3 and vitamin A are added right before pasteurization. That sudden jump to 15% of your daily value is absolutely critical. Why? Because the calcium in milk literally cannot be absorbed by your bones without adequate vitamin D being present. It's a total game changer. Finally, let's step into Section 5, Hormones and Health Claims. First up, the concern over hormones natively found in cow's milk. Yes, milk does naturally contain trace hormones like estrogen, but we really need some mathematical context here. Research shows that premenopausal women naturally produce at least 35,000 times as much estrogen daily as what is found in a single serving of 2% milk. To put that into perspective, 3 whole servings of milk contain less than 0.1% of the daily estrogen naturally produced by the human body. So, the crucial point is that even those tiny trace amounts of hormones natively found in milk are of low bioavailability. Because you're ingesting them orally, your digestive system essentially neutralizes them before they can ever fully absorb into your bloodstream and actually affect your human physiology. And that brings us to the second major debate, the rising trend of raw milk. This is milk that has skipped the pasteurization and homogenization steps entirely. Looking objectively at the data, observational studies do link raw milk consumption to minor reductions in childhood asthma and allergies. However, the documented risks are severe. Raw milk carries a very high risk of contamination from dangerous pathogens like Campylobacter, E. coli, and Listeria. The official consensus from the CDC is clear. For the vast majority of people, and especially for children and the elderly, the severe risk of bacterial infection heavily outweighs the potential benefits. So, we've broken down the proteins, we've navigated the lactose, followed the intense physical filtration, checked the added vitamins, and weighed the objective data on hormones and raw milk. It is a surprisingly complex liquid, isn't it? And it leaves me with one final thought for you. Armed with this brand new structural understanding of exactly what is happening at a microscopic level, with all the science poured into every single glass, what kind of milk will you reach for on your very next grocery trip?